My name is Yuan, and today I'm going to tell you how simple testing can prevent some of the most critical failures in distributed systems. And this is a collaboration with my colleagues from University of Toronto. And in this work, we thoroughly analyzed hundreds of real-world failures in distributed systems. And today, I'm going to talk about 3 key findings. First, these failures are indeed the result of complex sequence of events. But for the most catastrophic failures, they are almost entirely caused by incorrect error handling. And surprisingly, many of the bugs in the error handling logic are extremely trivial, that they are simply violating some good programming practices. We further built a simple checker to detect these bugs, and it gave us over 100 new bugs and bad practices that had been confirmed or fixed by the developers. So we know that failures in distributed systems can be deadly. So for example, in 2011, an Amazon AWS outage took down Reddit, Quora, Foursquare, Instagram, Netflix, and about 70 other websites. And last year, there's a brief Google outage that made the internet traffic drop by 40%. And in this summer, Facebook went down for 30 minutes, and some of its users called 911. Then the natural question is, why do these systems fail? Well, in an attempt to answer this question, we have analyzed hundreds of real-world failures. And specifically, we want to understand the end-to-end failure propagation sequence. By that, we mean that we want to understand the failure lifecycle that is started from faults that are the root causes, such as a bug or misconfiguration or a hardware fault. And once it's triggered, it will manifest into an error or an exception where the system starts to misbehave, such as a system call return error. And it might further manifest into a failure where it starts to be visible to the users or the administrators. Now, by understanding this end-to-end sequence, it allows us to identify the minimum conditions to expose these failures, and also reveal the weakest link along this sequence for one to break in order to prevent these failures. And this is in contrast to previous studies on distributed system failures, where they only examined each element in isolation. Now, to drive our study, we have selected 5 widely used open source distributed systems. And they are Cassandra, HBase, HDFS, Hadoop MapReduce, and Redis. And we randomly sampled 198 user-reported failures from the online bug tracking database from these systems. And for each failure, we carefully studied the discussion between the developers and the users and the related code and patch. And we ended up in reproducing 73 of them just so we could understand them. Well, not every failure will have the same criticality. And some of the failures, they will affect all or a majority of the users, and we call them catastrophic failure. But for example, if a failure takes down only 1 or 2 servers or only affect 1 or 2 users, it is not catastrophic failure. But if a failure takes down the entire cluster, it is classified as catastrophic failure. And there are 48 of the failures in our sample set are catastrophic. We further study them specifically because they have the most serious consequence. So next, I'm going to talk in more detail about our findings, that indeed these failures are the result of complex sequence of events, but for the most catastrophic ones, they are almost entirely caused by incorrect error handling. And many of the bugs are so trivial that we further built a simple checker to detect them. Now, I'm going to use one real-world example to show you the complexity of this failure. And in this case, a user reported that there's a sudden outage to the HBase cluster. And the HBase is this NoSQL database. It has a master and slave architecture where the slaves are responsible to serve and store user data, which is called a region. Now, to expose this failure, the first event we need is a load balancing operation where a region is transferred from an overloaded slave to a more idle slave. Now, once this slave B opens this region, it will further notify the master, and then the master will try to delete a zookeeper node, which is used to indicate that this region is currently being opened. Now, if right after this zookeeper node is deleted, there's another event where the slave B crashes, then the master will try to assign this region to another slave and will trigger the same operations where this slave will open this region and notify the master. And then the master will trigger the same code path and try to delete this zookeeper node. But this time, this delete zookeeper node will throw an exception because this node has already been deleted. But unfortunately, the error handling of this exception will bluntly take down the entire cluster. And later, developers fixed this bug by replacing this cluster abort with proper handling. Now we can make several observations from this example. First, it requires more than one input event to trigger. In this case, we first need a load balancing event followed by a server crash. And in fact, in a vast majority of the failure we studied, they require multiple events to trigger. And in addition, some of the events, such as this load balancing event, will only occur on long-running systems. So this indicates that to expose these failures, we need to combine stress testing with some other testing techniques, such as fault injection in this case. Now furthermore, the orders of the events also matters, that in a vast majority of the failures that require multiple events to trigger, they will only manifest in one specific order. Now in this HBase example, if we reverse the order of these two events, the failures simply won't occur. But sometimes, even given the right sequence of event, you are not guaranteed that the failure will occur. In many of the cases, there's a further timing constraint between these events. So in this HBase example, the second event where the slave B crashes have to occur after the zookeeper node has been deleted. And if it occurred too early, then the failure simply won't occur. Now I have shown you that these failures are indeed the result of some complex sequence of events. And this is perhaps not surprising because these systems already undergo through some thorough testing. So for example, it is required that for every patch, it has to be accompanied by a unit test. And these unit test cases will be run on every check-in. And they also use some static checkers, such as findbugs, that already includes over 400 of checks. And they also have their own fault injection testing tools. And in addition, these systems are also designed to provide high availability. So for example, they all have mechanisms to prevent one node failure to take down the entire cluster. Then why the failures, some of the failures are still catastrophic, that they affect our majority of the users? Now, if we break down these failures, we'll first see that almost all of the catastrophic failures, or 92%, are the result of incorrect error handling. Now, in these cases, there's initially one or multiple faults, and they will eventually trigger an explicitly detected error in the software. But in a vast majority of these cases, unfortunately, these errors are not correctly handled and result in a catastrophic failure. Well, this high percentage might sound surprising initially, but as an afterthought, they are quite intuitive because this error handling code is often the last line of defense, that they are there exactly to prevent such catastrophic failure from occurring. But we further zoom in to these incorrect error handling bugs, we found that more than 1/3 of them belong to one of the three simple patterns. Specifically, a lot of the errors are simply detected but ignored. And this pattern actually resulted in a quarter of the catastrophic failures. And there's another pattern. The system simply aborts on an overcount exception. By that, we mean that there are multiple exceptions that can be handled by one exception handling code, and it further aborts the system. And in all of these cases, that this system abort is the only intended reaction to one of the exceptions, but it will accidentally take down the system on other exceptions. And the last pattern is that in the error handling code, there's simply a to-do in the comment. And here I'll show you an example. Now, an angry user of MapReduce reported that MapReduce job Zhang on a rare resource manager restarts. And he had to SSH into every single node in his 4,000 cluster to kill all the jobs. And the root cause is these 4 lines of code, that when there's a reboot exception occurs, it's simply logged and further ignored. And later, the developers fixed this bug by adding the appropriate error handling and remove this to-do comment. Well, in another category, the bugs in the error handling code is system-specific, but they are still easily detectable because they are completely wrong. By that, it means that even code reviews or any test cases that as long as it can trigger this error handling code can reveal these failures. And if you still recall the previous HBase example, it is such a case that the error handling code of this keeper exception is completely wrong, that it should not take down the entire cluster. Well, this failure is extremely difficult to trigger, but the errors in the error handling code is obvious. Now, the remaining bugs are indeed complex bugs in the error handling code, but if we just look at the number of trivial mistakes and the easily detectable bugs, they actually account for over half of today's catastrophic failures. Then to further validate our findings, we built a simple static checker called Aspirator to detect such mistakes. So it's an extremely simple tool that works on Java bytecode. That for every catch block, it checks for 3 rules. That it should not be empty or simply contain a log printing statement. It should not abort if it catches multiple exceptions. And finally, the corresponding source code cannot contain to-do or fix me in the comment. And there are some false positive suppression techniques in our paper. Right? So if Aspirator has been used on the system, on the failures we studied, then actually over 1/3 of the catastrophic failures could have been prevented, given the identified bug is being fixed. Now we further applied Aspirator on 9 real-world systems. 4 of them are the Java systems that we included in our study, and 5 of them are the new system we did not study as a blind test for the generality of our findings. And for each warning that Aspirator reported, we look at the related code and try to classify into one of 3 types. We classify this as a bug if we can definitively infer that it will lead to some unexpected failure consequence. And on the other hand, if we can infer that it will not lead to any consequence, then we will classify it as false positive. And for the remaining cases, they are suspicious, but without domain knowledge, we cannot conclude the actual consequence, so we conservatively classify them as bad practices. Now here's the result, that you can see Aspirator had found 121 new bugs and 379 bad practices from these 9 systems. And in addition, it found new bugs in every systems we checked, indicating that the findings are not only specific to the systems we studied. And many of the bugs can indeed lead to some catastrophic failure. For example, if during the lock release it throws an exception and is subsequently ignored, it can lead to a deadlock and sometimes a cluster hang. And some bugs could lead to data loss. For example, during the journal recovery of a file system, if it throws an exception and subsequently ignored, then it could lead to an inconsistent file system. And finally, some of the bugs will lead to cluster crash, such as all the bugs that found by our aborting overcatch check. And we reported 171 new bugs and bad practices to the developers of these systems. And we have received mixed feedback. So 143 of them are already confirmed or fixed, but 17 of them are rejected. And we further classify them as false positives in the previous table. And we received some positive feedback, including that no one would have looked at this hidden feature, and ignoring exceptions there is exactly bad for that reason. Or I really want to fix the issues in this line because I really want us to use exceptions properly and never ignore them. But we also received negative feedback, such as I fail to see the reason to handle every exception. Then this raises the question that why there are so many cases that developers ignore the error handling. Well, we observed 3 possible reasons. The first is that developers may think that errors will never happen, so that they ignore them, such as illustrated by the comment of this case. Right? However, we still argue that it's a dangerous practice because later code evolution might enable these errors. And there are many cases we actually found such judgment is simply wrong, that the error could have happened. And also that error handling can be difficult, especially for those that are thrown by third-party libraries that are not well documented. Now in this code snippet, for example, the developer is complaining that God is not helping him to understand the exception. And finally, it's unfortunate that in many cases, feature development is prioritized over error handling. So there are some other findings in our paper that I do not have time to zoom into. So for example, we found that for these production failures, you do not need a large cluster to reproduce them. In fact, these failures, almost all the failures, are guaranteed to manifest on 3 nodes or less. And also that these production failures can actually be quite simply reproduced offline. In many cases, can be reproduced by unit test. And the corresponding system logs contains rich information. For example, they contain all the input events that trigger the failure. And on Wednesday, my student will give a talk on how we can automatically infer the performance information from these system logs. And finally, even more than half of the non-deterministic failures can still be deterministically reproduced by carefully constructed unit tests. So now if we look at each problem in isolation, I have told you nothing new. It is well known that error handling is often buggy. But by putting things together, we found that these incorrect error handlings is becoming the dominating cause of today's distributed, the catastrophic failures in today's distributed systems. And many of the bugs are extremely trivial. Now in conclusion, I have showed you analysis on hundreds of real-world failures to distributed systems. And we have found that these failures are indeed complex, that they are the result of complex sequence of events. But for the most catastrophic failures, they are almost entirely caused by incorrect error handling. And many of the bugs are extremely trivial, that they simply violate 3 patterns, that they either ignore the exception, or they abort the system on an overcaught exception, or they contain to-do in the comment. Right? And we further built an embarrassingly simple tool, Aspirator, to detect such trivial mistakes and gave us a lot of new real-world bugs. So I will end my talk with some of the comments in the error handling code that is detected by Aspirator. We probably can write a book on these comments. Right? And that's all for my talk, and thank you.
We have time for some questions.
Sure.
Stefan from Google. Can you go back to some of the slides that show some Java code?
Sure.
A bit before.
Like this one?
Yeah, for example. I mean, in Java, checked exceptions are a notoriously controversial feature. Have you looked at any correlation between these overcatches and the fact that these are checked exceptions? As in, it's a pain in the ass if you don't do something like just catch it and drop it on the floor.
Okay.
I mean, the other one that you probably look at and consider as a bad practice would be to catch that no transition exception and then turn it into a runtime exception of some random kind.
Mm-hmm. That's definitely an interesting discussion, this interesting question. So sure, we observe a lot of these errors or exceptions are ignored exactly because they are checked exceptions. So the compiler enforces the programmers, you have to catch those. However, in terms of whether you want to ignore them, you can do the same on unchecked exceptions, or in C, for example, you do not have to even check for a system called return error. So in terms of ignoring the exception, I think if you want to ignore it, it's the same. But we do find from a tools designer's perspective, such as our perspective, by enforcing you to catch every exception, significantly opens opportunities for us to build the tools to check them, because we know clearly where are the error cases. Whereas if it's like in C, we probably have a harder time to know where are the error cases.
Hi, I'm Fred Douglas, EMC. So I'm curious about the false positives. You seem to have almost as many false positives as you had confirmed bugs. And can you give some insight into what sort of things you were finding that were tripping you up and whether there are things you can do to improve on that?
Sure. I can give you actually one of the common false positives we had. It's reflection-related exceptions, right? So in Java, actually a lot of the false positives are coming from these practices. That in Java, you can use reflection, that you can speculate what's the type of the class. At runtime, it may not be that type of class. It does not contain certain field or certain method. It's okay. And in many cases, it's desirable to just let the system go on. In many cases, they will try for another type. And this is one dominating example of false positive. It actually contributed a lot of these cases. And some other cases, you can imagine that, for example, if you cannot find a file, it will throw an exception. Maybe it's okay, and you can go on to find for other files. So these are pretty much system-specific semantics.
Margot Seltzer from Harvard University. So I love this study. I love your results. I think everyone should do better error checking. I just want to take issue with the, you should never say this can never happen. I think aborting in cases where the developer really believes something should never happen is a vital thing to do, because we all build assumptions into our system, and if we don't explicitly code what those assumptions are, a lot of times you can't recover from errors that you think shouldn't happen. So I actually think it's really important that you document that you think things can't happen and you abort when things can't happen, because that's the only way you're going to figure out why your assumptions are wrong and how the system has changed to subvert them. So I don't want to discourage people from saying that this should never happen and aborting.
Well, thanks for your comment, and you're absolutely right that whenever you have an exception, especially for those exceptions where developer thinks it will never happen, we argue that it's better to program aggressively in terms of abort it right away, fail right at its place, preventing it from propagation, rather than ignoring it and leading to some unexpected result. But I do want to clarify one thing, is that for our pattern where aborting overcatch, all of those cases, the exception that contains abort are overcatches, that they are intended for one exception, but because it's overcatch, so some unexpected exception will fall into that and take down the cluster.
Hello, I'm Kautar from IBM Research. Thank you, this is great work. So my question is, from the study that you've done, do you think, the problem of ignoring these exceptions can be somehow, solved by automatically trying to, solve these things using either static or dynamic program analysis, especially for the trivial, exceptions that you've seen?
So you're asking whether we should free the developers from the burden of handling exceptions, but rather automatically
fill
handle
the
them.
gaps, not.
I have to say that I'm skeptical about that idea, because error handling is just messy. It's just difficult, as we have seen from many of the examples. I think it already creates all these burdens to the developers. I don't know whether automatically handling them can be a good thing or maybe result in some even more mysterious or catastrophic failures.
Hi, I'm Pepe from NC State. I'm interested in the 8% of the bugs that is not that there's no error handling. Can you explain a bit about it?
Sure. So in that 8%, indeed, there was a silent error that was never even detected by the developers. For example, one of the case was that, there was this, actually, one of the few cases is that the server, they, let me think. Yeah, for example, there was actually, in Redis, there was this failure that I think the epoch system call, if you have too many file descriptors, it can return an error, but it was just simply never even checked by the developers. So it wasn't detected, so we classify as undetected error.
Do you think might be like some like error masking in the lower level be a factor of this uncaptured error?
That's an interesting question. Well, I guess the question boils down to at which layer in the software stack is responsible to handle the error. I guess it's hard to say. I mean, I guess the error eventually should be returned to whoever whichever layer that has the most power, best knowledge to handle these errors. I'm not sure whether silently handling these errors and masking them from developers is a good idea. And I think on the contrary, probably it's better for the library designers to just return the error to the developers and probably ask the developers to handle it. But I mean, this to me is a quite profound question, so I really don't know the answer.
Okay, thanks.
Yeah.
Last question, very short.
Hi, yeah, I'll be brief, thank you. Jonathan Bell, Columbia University. Love the work, love the study, especially all the bugs you found. I understand and appreciate how difficult it is to do a study like that. I was curious if you compared your tool Aspirator to find bugs, the popular Java static analysis tool. Yeah,
that's a good question. Indeed, actually, these systems, they already use find bugs.
Yeah.
And so find bugs contains, I think, 400 or some checks.
Right.
But we are actually surprised that they don't have checks for these simple patterns.
I see.
But if you're asking that whether we should implement in find bugs, absolutely.
Well, I was curious particularly, I'm sorry, if find bugs found these errors also.
I do not think so.
I see. Okay, cool. Thank you.
Thank you.